Hello, this is LeGM's podcast. Think about it for a second. We rely on batteries for, well, almost everything. Your phone, your car, your laptop. They're just powering our lives. But beyond, seeing a percentage on a screen or maybe wondering if your car will start on a really cold morning, how much do you truly know about what's going on inside them? Like what makes them tick? Or maybe more importantly, what makes them stop ticking? Our mission today on this deep dive is to kind of pull back that curtain. We're going to try and equip you with the knowledge to understand, maybe test, and even troubleshoot batteries like an expert. Get ready, because we might uncover some surprising facts and hopefully give you some practical insights that go way beyond just looking at a simple number.
Yeah, absolutely. We're really going to try and bridge that gap, between just seeing a percentage and actually understanding what's happening. We'll start with some practical stuff like hands-on battery testing methods, especially for vehicles. Then we'll peel back the layers a bit, look at the fundamental science behind different battery types. You'll learn exactly how they charge and discharge and what all those acronyms you might have heard, like CCA, SOC, SOH, what they really mean for a battery's health and, its performance.
Okay, let's unpack this then. To really ground this conversation, let's start where a lot of us have direct experience. The car battery, we often just focus on its voltage, right? But there's clearly a whole lot more to its story.
Indeed. Yeah, voltage is just one piece. To truly assess a battery, especially in a car, you really need a specialized battery tester. There are models out there. Something like a Micro 200 Pro is pretty effective. Its basic function is quite straightforward, actually. You just connect the red clamp to the positive terminal, the plus, and the black clamp to the negative, the minus. And these testers can usually handle both 12-volt and 24-volt batteries.
Okay, so once it's hooked up, what's the very first thing it tells us? Or maybe what's the most critical piece of information we need to input? Is it just voltage or something more, nuanced?
Well, voltage is there, but the really critical input is usually the CCA, the cold cranking amps. That number tells you about the battery's ability to start an engine, especially when it's cold, right? It represents how much current that battery can deliver under those tough conditions, like freezing temperatures. So that's often the first crucial setting you'll punch into the tester. Let's look at an example we examined. There was this Rocket Battery ADL. It was specified on the label to have 660 CCA. When tested, its initial voltage read 13.10 volts. Now, for a 12-volt battery, anything above, say, 12.5 V up to that kind of reading usually indicates good voltage. It looks fine on the surface. And the state of charge, the SOXY, it was at 98%. That means it was really well charged, probably from being driven recently.
Right, and this is exactly where I think common assumptions just get shattered. Most of us, myself included, would look at good voltage, high charge, and think, okay, this battery's great. But the tester flagged it for battery replacement. So why? Why is voltage so misleading here? What's the hidden signal we should be looking for?
That's the absolute key point. Even with that good voltage, that high SOS, the tested CCA was only 350. That's way, way lower than its specified 660.
Wow, okay.
So what does that imply? It means it probably wouldn't reliably start an engine in winter, despite what the voltage reading suggests, and maybe even more importantly, the state of health, or SOH, that was down at a mere 21%.
21%.
Yeah. SOH basically represents the battery's overall health, kind of like its health percentage. And honestly, anything below 50% is generally considered problematic. And one more thing, its internal resistance, R, was 9.88.
9.88. Okay, what does that number actually mean in practical terms? Like, is that good or bad?
Oh, it's bad. Think of battery resistance like a clogged pipe. An ideal healthy battery has an internal resistance somewhere between 3 and 6.
Yeah.
That lets the power flow freely. But this battery was at 9.88. That's like a severely clogged pipe. It means it struggles to deliver the power needed, especially when you demand a lot from it, like, starting a cold engine. So even if the voltage looks good and it seems fully charged, that critically low SOH and CCA, combined with the high resistance, well, it signals a battery right at the end of its useful life. And this connects directly to that common experience we all dread, right? A seemingly fine battery just suddenly failing when the first cold snap hits.
Okay, so it sounds like voltage is almost useless on its own then, for predicting failure at least. But if these testers are so much better, why do car mechanics sometimes still just check the voltage? Is it just speed?
That's a great question. And yeah, speed and simplicity are definitely part of it. For really quick, is it dead right now? Check, voltage can give you a hint, sure. But for a true health assessment, especially if you want to predict future failure, you absolutely need a tester that gives you CCA, SOH, and resistance readings. It's just a much deeper look. Let's contrast that first battery with a good battery example we looked at. This one was specified at 620 CCA, and it tested at 520 CCA. Now, that's a slight drop from the specs, sure, but it's well within acceptable limits. It wouldn't affect cold starts.
Right.
Its voltage was 12.37 V, even after sitting for a month with no operation, which is still considered pretty normal. The resistance, 5.73, nicely within that ideal 3 to 6 range.
Much better.
Exactly. Its SOK was 61%, which is lower because it hadn't been used, but again, completely normal for an inactive battery. And crucially, its SOH was 70%. That indicates really good health. So you can clearly see why relying only on voltage can be incredibly misleading, can't you? CCA and SOH are really paramount for a true battery assessment.
Absolutely. And the good news here is these testers, they aren't crazy expensive, right? They're quite accessible.
Yeah, exactly. You can often find them online for maybe the equivalent of $30, $40 US. It's a pretty small investment for the kind of insight you get.
Definitely. It seems like a great tool to have, whether you're checking your own car, maybe even looking at a used car or a battery you're thinking of buying. I've definitely had that moment. First cold snap, you turn the key and just click, nothing. Now I know it probably wasn't just bad luck. It was likely a critically low SOH I just didn't know about. Okay, so with a solid grasp of car batteries, let's shift gears a bit. Let's talk about the smaller but, equally vital powerhouses in our everyday devices. What exactly are they made of? What are the different chemistries?
Right. So when we talk about modern rechargeable batteries, the ones in your phone, your laptop, your earbuds, we're largely talking about lithium-based types. The main ones you'll encounter are lithium-ion, Li-ion, lithium polymer, Li-ion, and maybe lithium iron phosphate, LiPo4, although the last one's often for bigger things. Lithium-ion or Li-ion batteries are super common. They typically have an output voltage around 3.7 volts. Their big advantages are high energy density, meaning lots of power in a small package, a pretty wide operating temperature range, like -55°C all the way up to 85°C, and a decent life cycle. However, the sort of classic Li-ion uses a liquid electrolyte, and that carries some risks, like potential leakage and, in very rare cases, even explosion or fire. Plus, their cell designs are often limited to cylindrical shapes, like those little AA-sized ones, just bigger.
Okay, so with all those advantages of Li-ion, I'm curious, why did lithium polymer even need to be developed? What was the key problem it solved? Especially when you think about how thin and sleek our phones and laptops have become.
That's an excellent question, and it hits right on the motivation for LiPo. Lithium polymer batteries were developed specifically to keep the good performance of Li-ion, but tackle those drawbacks, primarily the safety concerns and the design limitations. They do this by using a stable, non-liquid electrolyte. It's usually a solid or maybe a gel-like polymer.
Ah, okay, no liquid.
Exactly. That basically eliminates the risks of leakage and explosion associated with the liquid. And a major advantage of LiPo is the design flexibility it gives manufacturers. They can be made incredibly thin, like down to 3 millimeters sometimes, and in all sorts of custom shapes. This allows for those really innovative, sleek device designs we see everywhere.
Makes sense.
But there's always a trade-off, right? While LiPo batteries solve those key safety and design issues with the non-liquid electrolyte, here's the flip side. They tend to be more complex and therefore more expensive to manufacture. They also might have a slightly lower energy density compared to a similarly sized traditional ion, and sometimes their performance isn't quite as good at very low temperatures.
So that super thin, flexible battery in my phone might come at a bit of a manufacturing cost and maybe a tiny compromise on, say, extreme cold performance compared to a bulkier Li-ion.
Pretty much, yeah, it's a balance. And then briefly, there's lithium iron phosphate, LiPo4. You probably won't find these in your smartphone, not usually, but they're gaining huge traction in larger applications. Think electric buses, big home energy storage systems, some golf carts, even some newer electric vehicles are using them.
Why is that?
Because they offer an incredible cycle life. They can be charged and discharged thousands more times than standard Li-ion. Plus, they are inherently safer, much less prone to thermal runaway. This makes them ideal where long-term durability and minimizing fire risk are really big concerns.
Fascinating. So knowing about these different chemistries is one thing, but how do these amazing little power sources actually get charged? It's not just like flipping a switch and pumping electricity in, is it?
No, definitely not. It's actually a carefully managed process, especially for lithium-ion-based batteries. Charging generally follows a specific curve with 3 distinct stages. The first stage is often called pre-charge or trickle charge. This is for batteries that are really deeply discharged, maybe down in the 2-3 volt range.
Like waking it up gently?
Exactly. The water droplets falling analogy is pretty good here. It's like gently nudging a battery that's really, really low on power, say below 3 volts. In this stage, a very small current, maybe only a tenth of the normal charging current, is applied. This slowly brings the battery back up to a safe voltage level without stressing it. Then once it's safely awake, and above that, maybe 3-volt threshold, it transitions into the main phase. Constant current, or CC. This is the rapid charging phase. Here, the battery receives a steady, relatively high current. Think of it like filling up a swimming pool quickly with a hose turned on full.
Okay, makes sense.
Finally, as the battery voltage gets close to full charge, typically around 4.2 volts for most Li-ion, it enters the constant voltage, or CV stage. In this final phase, the charging system holds the voltage steady at about 4.2 V, and the charging current starts to gradually decrease. It keeps tapering off until the current drops below a certain small threshold, and that signals to the charger that the battery is fully charged. And all through this, there's usually an internal charging IC, an integrated circuit that's constantly monitoring the voltage, the current, and often the battery temperature too, just to make sure everything stays safe and optimal.
Wow, that's a lot more sophisticated than I would have guessed for something I just, plug into the wall every night. Very cool. And what about the other side of the coin? Using the battery, how does it discharge? Is that just a simple straight line down from full to empty?
Not quite, no. The discharge curve for Li-ion batteries also has a distinct shape. When it's fully charged, the battery voltage is typically above 4 volts, maybe 4.1 or 4.2. But the most significant portion of its usable life, say from about 80% charge down to maybe 20% remaining capacity, happens where the voltage stays relatively stable. It hovers around 3.7 volts for a lot of that time.
Ah, okay.
And this stable voltage point, that 3.7 V area, is known as the nominal voltage, or sometimes the rated voltage of the battery. It's kind of its comfortable operating zone. However, once the capacity drops below about 20%, the voltage starts to fall off much more rapidly. That's the signal that the battery is getting close to being fully discharged.
Got it. So all these technical terms, voltage, CCA, SOH, SOV, different chemistries, charging curves, how do they all tie together into practical performance for us, the user? What are the key terms that really define a battery's capacity and health?
Right, let's boil it down. One absolutely fundamental term is mAh, which stands for milliampere hour. This is the standard unit for battery capacity. It basically tells you the amount of electrical charge the battery can hold or how much current it can supply over time. So for instance, a 1,000 milliampere battery can theoretically supply 2,000 milliamperes, which is 1 ampere, for exactly 1 hour. Or to put it more practically, if you have that same 1,000 milliamp battery and it's powering a device that only draws 200 milliA, it should last for about 5 hours, right? 1,000 milliamp, 200 milliamp, 5/8.
Simple math, okay.
Another really important concept, especially when talking about charging and discharging speeds, is the C rate. The C here stands for capacity. The C rate indicates how fast a battery is charged or discharged relative to its maximum capacity. So a 1C rate means charging or discharging the battery at a current equal to its capacity, completing the process in 1 hour. For our 1,000 mil battery example, a 1C charge would mean charging it at 1,000 mA. It's generally recommended, for longevity and safety, that basic charging should be done at 1C or less. Often you'll see recommendations in the 0.5C to 0.7C range for everyday charging. Faster charging usually means higher C rates, but can sometimes stress the battery more.
Interesting. We touched on CC briefly with car batteries, but let's dive a bit deeper because it's definitely distinct from SOH, and both sound critical for any battery, phone, or car. Can you clarify again for all our devices, what exactly is state of charge, and how does it differ fundamentally from state of health?
Yes, absolutely crucial distinction. Let's nail this down. State of charge, or CIRCE, is essentially the percentage of the battery's current remaining capacity compared to its total possible capacity right now. So if your smartphone shows 80% battery life remaining, that's its SOCI.
Like the fuel gauge.
Exactly.
Yeah.
Think of SOCI as the fuel gauge in your car. It tells you how much gas you have in the tank right now. Its importance is huge, obviously. For users, it tells us when we need to charge our devices. For electric vehicles, it's absolutely critical for predicting driving range. And from a safety perspective, managing SOCI helps prevent dangerous overcharging or over-discharging.
Okay, fuel gauge. Got it. So what's SOH again?
Right. State of health, or SOH, on the other hand, is more like maybe the engine's overall condition report from a mechanic. It tells you about the battery's overall health and its ability to store and deliver energy compared to when it was brand new.
So it degrades over time.
Precisely. SOH reflects the aging process of the battery. A brand new battery has 100% SOH. As it gets used, charged, and discharged hundreds of times, its SOH gradually decreases. So while SOC tells you the current charge level, fuel gauge, SOH tells you about the battery's long-term condition and how much life it realistically has left, engine health. Both are vital, but they measure different things.
That clears it up nicely. So C is now SOH's overall lifespan.
You got it. And just one more piece of the puzzle. We've talked about individual cells and their chemistry, but often manufacturers need more voltage or more capacity than a single cell can provide. That's where connecting cells together comes in, either in series or parallel. Connecting cells in series S means linking them positive to negative, positive to negative. This increases the total output voltage. So if you see a battery pack labeled 2S1P, it means two cells are connected in series, doubling the voltage, and there's just one set of those in parallel.
Okay, series for more volts.
Right. And connecting cells in parallel P means linking all the positive terminals together and all the negative terminals together. This increases the total current capacity, Ma2BNO. So 1S2P would mean one cell in terms of voltage, 1S, but two cells connected side by side in parallel 2P, effectively doubling the available milliamp hours or runtime. You often see combinations like 3S2P or 4S1P in larger battery packs.
What an incredible journey, really, into the heart of these batteries. From, decoding those baffling acronyms like CCA and SOH that seemed so technical before, to understanding why our phones charge the way they do. It's really clear there's so much more going on than meets the eye. I feel like I've just unlocked a whole new level of understanding about something I literally interact with every single day.
Absolutely. And hopefully that knowledge feels empowering. Knowing about battery health really does go far beyond just glancing at a voltage reading or a percentage sign. Understanding these deeper metrics, SOH, CCA, C rates, and the different types of batteries, it can truly give you a clearer picture of what's happening beneath the surface of your devices and maybe help you take better care of them too.
Yeah, this deep dive has definitely transformed my understanding. I hope it empowers you, the listener, to look at your devices differently too, not just as these sort of black boxes, but with a deeper appreciation for the clever science powering them. So here's a final thought to mull over. With this newfound understanding of battery health and performance, consider how this knowledge might change not just how you, say, check your car battery next time, but also how you think about extending the life of all the rechargeable devices in your home. What small changes, maybe in charging habits or just awareness, could you make to keep your devices running longer and more efficiently? Something to think about.